T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Liftoff.
Welcome everyone to another episode of What's Up with the Universe. I'm your host, You Like You Who, and I want to welcome you to a little exciting journey we're having today. Today we're talking about exoplanets. Yes, they are very, very far away. And in case you about little distances and what that actually means, well, let's take a look at this here. Oops, wrong button here. We talk exoplanets, of course. Like I said, they're very, very far away. They're not within our own solar system. So this right here is basically about distance. The Milky Way itself. It's about 100,000 light years across. So what exactly is a light year? We're going to zoom in here on to our own little solar system for a moment. Because a light time is distance light travels within a specific period of time. 1 light second is equivalent to 186,000 miles away from the sun. We're going to start that as a base point. 1 light minute is 11 million miles away from the sun. And we even go further out past Earth because it takes 8 minutes for light to reach Earth, and it takes 1 light hour to reach past Jupiter, which is 671 million miles away. Yes, we're going past the Kuiper Belt. This is even further. It takes about, 1 light day will take about it's 116.1 billion miles away. We're going to even go past the Oort cloud. Beginning of the Oort cloud, it takes 29 light days to reach the Oort cloud. Of course, even further past the Oort cloud is 1 light year, which is 5.8 trillion miles away. And our closest planet and star is 4.25 light years away. That's Proxima Centauri. 100 light years is 588 trillion miles. As we go back out toward the Milky Way itself, we will see that the Milky Way is 100,000 light years across, which is equivalent to 588 quadrillion miles. Yeah. Exactly. So people ask, what exactly is an exoplanet? Well, it's a planet that orbits another star other than our own, also called an extrasolar planet. On average, it's estimated at least 1 planet for every star in the galaxy. Basically, if you look up at night and you see all the stars you can see, if you're able to see stars, about 1 out of every 3 or 4 planets, stars there, has a planet. What kind of planet that is yet to be determined to be. There are many different types of exoplanets. There's gas giants, there's Neptune-like planets, there are even Earth-sized planets. People want to know sometimes, hey, how are planets actually made? Well, it's a little thing called accretion. In 2003, NASA astronaut Stanley Love, Don Pettit, and NASA researcher Scott Messenger used the ISS to basically show how accretion works. And let's let astronaut Stanley Love explain exactly how this process works.
Here we have a gallon-sized plastic bag filled with 1 millimeter diameter sodium chloride crystals. You shake this up, and the individual crystals will rapidly form agglomerates, and these in turn form floccules of the order of several centimeters on the side, and all of this happens in about 10 seconds. Here is a slow motion view of the same thing, showing the individual crystals rapidly forming agglomerates. And again, these form floccules all within about 10 seconds.
This is how the universe, our
Here we
galaxy,
see
solar system was
a
formed.
2 to 3 centimeter sized agglomerate that is impacting your wall at about 1 centimeter per second, demonstrating a rather strong cohesiveness to hold together. And here we have sodium chloride crystals, 4 to 10 millimeters in diameter, and these exhibit the same traits as we saw with the smaller crystals. They rapidly coalesce and form agglomerates of floccules that are several centimeters on an edge.
In case you're wondering what aggregates were, it's basically a little concentrated material. This experiment basically told us how planets are formed. It's a springboard for new science and exploration here. Thank you, guys. This newborn planet right here is orbiting its little star, PDS-70. This is seen through the ESO's VLT, otherwise known as Very Large Telescope. This is an actual picture 370 light years from Earth. Yes, we can actually take a picture of exoplanets. And I'm going to tell you exactly some of the reasons or some of the methods that our scientists currently use to find exoplanets. One of the first ones, basically, I'm going to get to that in a minute, but one of the first ones actually discovered was in 1984. It was a planetary disk formed. It wasn't actually a planet itself. It was a disk formation. This picture right here shows the actual planet itself, but the disk itself is an exaggeration of what it is. This is Pictorius C63 C6C. It's 63 light years away, and it's not Pictures B, it's Pictorius B. Spell check. Sometimes I dislike it. And there goes one of my speakers. So these two guys right here, Swiss astronomers, Didier Quezel and Michel Mayor. These two discovered the pair 51 Pegasus B in 1995. This was the very first star that they found orbiting a very first planet they found orbiting a star like our own. And basically, what is 51 Pegasus B? Well, let's take a look at this. 51 Pegasus B, it's about half the size of Jupiter, and it orbits in about 4 days. I mean, the temperature is about 10,000 degrees Celsius or 18,000 degrees Fahrenheit. Yeah, it takes about 4 days for it to orbit the planet, and it's about 50 light years from Earth. Well, yeah, because of gravity. As far as Mountains Elysium says, sorry, let me show this real fast. As far as I know, planets begin with electrostatic attraction, then tips over time under gravity in its own acceleration. Yeah, astronaut Stanley Love actually did that with the electromagnetic. Yeah, basically what he was talking about was electromagnetic and analytical particles were being attracted to those small aggregates, which forms larger forms, larger lumps of planetary bodies. Let's see. Oh, I forgot to say hi to Mountains Elysium. Bee's Nest. The Earth is not flat. If the Earth is flat, then that means Mars is flat, Venus is flat, Uranus is flat. Let's get back to Pegasus 51b here. It is basically 47% has 47% less massive, but 50% larger than Jupiter, which means it's a lot heavier. It's just about 11% larger than our own sun. Like I stated earlier, there are basically 5 different ways to find an exoplanet that scientists currently use right now. One of the current ways is radio velocity, which means they're watching for a wobble. 820 exoplanets have been discovered using this method. Another way is called direct imaging, which means you just take a direct picture of it. 51 exoplanets have been found using this method. Another one is called the transit, searching for shadows. This has been the most popular method because 3,266 exoplanets have been found using the transit method. Gravitational microlensing. Yes, that may seem a little confusing to you, a little technical, but it's light in a gravity lens. I'm going to explain that. 101 exoplanets have been found using this method. Another method is called astrometry, which means minuscule movements. And so far, only one has been found using this method here. Mountains Elysium says Uranus may be flat, but mine isn't. Sorry, I couldn't help myself. Good one, dude. Okay, let's talk about these 5 ways. Sorry, that's funny. Let's talk about these 5 ways how scientists and astronomers find exoplanets. The first one is radial velocity. This little diagram here is a basic representation of the Doppler effect. You can see the method working in the animation right here. It causes the planet's stars to wobble around its orbit as the planet moves to and from. You can see the light stretches. When it goes blue, it's closer. Red is farther away. Basic Doppler effect method. I mean, orbiting planets, they cause stars to wobble in space. It actually changes the light color they observe. Excuse me. I mean, one way to make sense of this gravitational interaction between the planet and the star, imagine a game of tug of war. Who's going to win? Well, yeah, they both kind of like evenly win, but stars basically win on the long run because they are more heavy than more massive with gravity. But even though the planet is small, it still has enough gravitational force to make an effect on the planet itself. Here at this diagram, things may look normal, but there's a big star and a small planet, and the small planet orbits the big star. Look how the star is moving a little bit. I mean, this, of course, the animation is exaggerated, but this is what happens when a star wobbles. It can tell us if the star has a planet, how many they are, and how big they are by the amount of wobble that the planet and the star attract upon each other. Transit. Another method is searching for shadows. Yeah. You can see the graph right here on the bottom of the screen. When it basically is measuring the light. And when the planet passes in front of it, you can see the light will be slowly dipping. This will it's called a light curve. It's basically when the planet passes in front of the star, it blocks some of its light. It will actually indicate the dropness in the brightness. And when it does multiple times, that's how astronomers basically discover if that's actually a planet or not. Of course, the transit method isn't just for finding planets. It can also give information about the planet's composition and the atmosphere. Yeah, we can tell what kind of atmosphere a planet has. Yeah, they did find another method using X-ray transit. Anton Pevov had a video about it. I did not pull that up yet, but I'm getting to other transits here. That's a good one, Mountains. Thank you. See, science should be free and knowledgeable. Nobody should ever charge for any kind of science information. This is why I love to post this stuff. Okay, where I was for a second. The farther the planet goes away, the longer it takes to orbit the pass in front of the star. So the longer the transit event lasts, the farther away the planet is from its own host star. Here's the little tricky part. When you see multiple planets, you see light that gets curved, gets complicated when more planets pass in front of the star. This just basically takes a lot more work for astronomers to pick out each planet in the data, because as you can see, as the graph right here on the bottom, when one planet passes in front of the star, the light dips. Another planet passes in front of the star, the light dips even less. But if it's smaller or a larger planet, it even dip even more. This is a little hard discerning because there was once recently a star discovered which had the exact same effect. It had multiple dips on it. Astronomers are confused if it was an asteroid broken up or if it was an artificial Dyson sphere or something. This still has not yet to be determined, but I believe that astronomers are basically consenting that it's a debris field of asteroids that are passing in front of the star that are orbiting it. Another method that has been discovered, which 551 planets were, is called the direct imaging. Yep, that means taking a direct picture. You can't take your cell phone out and take a direct picture of an exoplanet. It's a little far away. There's basically two methods right here, popular methods that astronomers use to take direct imaging. They call it light blocking. One part is called the coronagraphy. It's a device used inside the telescope to block light from the star before it reaches the telescope detector. I mean, they're built on internal add-ons, and they're using directly now to use direct exoplanets from ground-based observations like the LTO, the VLT, Very Large Telescope. Yeah, they have just discovered another planet. They have, I think they have an Andromeda system, and another one, the one south of Andromeda. I forgot the name of it. Sorry about that, people. Hey, Mountains, if you have the information, put it in the description below wherever they can check it out. That's what it's for. Let's see, but in the transit methods, don't they have to be relatively large and close to the sun? Actually, no, they don't have to be relatively large and closer to the sun. As the diagram stated before, let me go back to the diagram and I'll actually show you, okay? Go back a couple pages here. This diagram with multiple different rates, different sized planets, different directions. The bigger the planet is, the bigger the dip. But the planet's farther away, the smaller the dip. They actually can determine this by the light that is being taken away from the sun. And they can also use spectrometers to find out what the actual planet consists of. We are talking about, oh yeah, my second favorite direct imaging, coronagraphy. Besides coronagraphy, is the star shade. Well, sorry, star shade. There's no official name for it, but it's called the star shade. What is the star shade? It's a device that's basically positioned in front of the telescope that blocks out the sun. I mean, it's perfect. I love it. It's wonderful. Another method is called gravitational microlensing. Light in a gravity lens. I mean, as you look at this diagram here, it's a basic explanation. You might think, wait a minute, I'm not Albert Einstein. How can I understand all these light curves and these waves bending right here? Well, I'm going to do this very easily simplified for you. Gravitational microlensing is light from a distant star that is bent and focused by gravity as the planet passes between the Earth. In other words, big objects warp the fabric of space. Plain and simple. This effect causes light to distort and change direction when affected by the gravity of a massive object like a star or a planet. Lensing event, it looks like a distant star that gets gradually brighter over a space of a month or so, then fades away. If a planet happens to be lensed, it looks like a bright blip of light that happens during the brightening and dimming process. Hopefully that was not the Albert Einstein explanation. Basically, big objects warp the fabric of space. That is gravitational microlensing, summed up. I mean, astronomers can't predict when or where these lensing events will happen. So they actually have to watch for over a long period of time in the sky. I mean, sometimes there are free-floating planets in space, the ones that do not orbit a star. These cause quick microlensing events that astronomers will record. Of course, these are called rogue planets in the galaxy. The animation shows what kind of events look like through a telescope if you're actually looking at this. Another method was called astrometry. Minuscule movements. Yes, little tiny minuscule movements. But before we talk about that, I want to put on Mountain's comment here. It was on Anton's video today. The X-ray transit was on a star in another galaxy. Awesome sauce. If you can put that link in the description, everybody can enjoy and watch and check it out. We most appreciate it, Mountain. Thank you. I love space news. The minuscule movements here, basically you see little tiny movements. And this is, in order to track the movement of these stars, scientists take a series of images of the star and sometimes the other stars that are near it in the sky. I mean, each picture they compare the distance between these reference stars and the star they're checking for exoplanets. So they have to look at other stars to find other little other planets on micromoving. What did you say? What did you say, Mountains? I would consider myself religious. That does not stop me from loving science. It enhances my faith, not diminishes it. I love to hear new discoveries. So do I. And especially when discoveries are proven wrong, I love it even more. Because any scientist will tell you, we want to be proven wrong. Is this right or not? That's science. Thank you, Mountains, for getting the link. We're going to talk about something else about exoplanets. One of the reasons why we're looking for them, because we're looking for the habitable zone. Planets are in the habitable zone, otherwise known as the Goldilocks zone. There are planets that are too hot, too cold, and just about right, which is highlighted in the green section there. Stars that are smaller and cooler and lower mass than our sun, which is an M-dwarf star, they have the habitable zone, which is much closer to the star than the sun, G-dwarf. Stars that are larger, hotter, and more massive than our own sun have the habitable zones much farther away from the sun. It makes more sense because the larger the star, the larger the heat, you want to be further away from it. You don't want to be really close up like Mercury. Our own solar system, there are 3 planets in the habitable zone. Yep, Venus, Mars, and Earth. If any extraterrestrial life was looking at our planet and looked at the habitable zones, they wouldn't see 3 of them. Which means that not every planet in the habitable zone has life on it. That is one of the tricky things about searching for extraterrestrial life, which SETI does. But here's some extra news for you guys. In February 22nd, 2017, NASA found the first most Earth-sized planets in the habitable zone around TRAPPIST-1. 7 habitable planets in the habitable zone possible, which is only 40 light years from Earth. You guys posted in the description below, Mountains. And I forgot how to make you a mod. Sorry about that, dude. I'll do that in a little bit. But yeah, 40 light years from Earth, TRAPPIST-1. It took 500 hours of exoplanet transit to discover these 7 planets right here. This is 500 hours of data from NASA itself. Of course, we cannot talk about exoplanet life without Francis Drake. The Drake equation. Okay, Mountains, just one moment. Let me see if I can get you a mod here for a second. Where are you, Mountains? 40 light years from Earth, TRAPPIST-1. Oops, sorry about the feedback. It's 500 hours. Sorry about that feedback. I'm trying to get Mountains a little wrench here so we can post some stuff. There you go, Mountains. Okay, we are talking about Francis Drake. He was born in May 28, 1930, and unfortunately recently died June 16th of this year. In 1972, he co-designed the Pioneer plaque with Carl Sagan. It was the first message that was actually sent into space. More about the Drake equation and Francis Drake. It was written in 1961, not for the purpose of quantifying the number of civilizations, but as a way to stimulate scientific dialogue at the first scientific meeting on the search for extraterrestrial intelligence. It wasn't saying, hey, this is how life exists, this is numbers. This is a possible equation. And this is the actual equation itself. M equals R times FP times NE times FI times FII times FC times L. I know, it's a mouthful. Let's break this down here. N, the number of technological advanced civilizations in the Milky Way galaxy. Well, so far we only know of 1, and that's us. That basically is the sum of life. R, the rate of formation of stars in a galaxy. We already know this. Fraction of stars with planetary systems. Well, we so far know a little about this. We have found over 4,000 exoplanets so far, which comes to the unknown equation here. We do not know this in what's past. NE is the number of planets per solar system with an environment suitable for life. We do not know all of these planets yet. And if you break it down even further to FL, fraction of suitable planets on which life actually appears. We still do not know this yet. FI, fraction of life bearing planets which intelligent life emerges. So far, we only know of 1. And here's the tricky part. FC, fractions of civilization that develop technologically that release detectable signs of the existence of the space. So far, that's still us. And the length of time. Such civilizations reach detectable signals into space. We still do not know this. It's still only us. You guys are probably wondering, hey, how can you join the exoplanet hunt? Well, NASA has a nice little program here. You can check out the Planet Patrol. Yes, be part of Planet Patrol. Help NASA discover exoplanets. They have various pictures posted, digital frames. Check it all out. Its age is 2 to 200. Anybody can help out NASA. This is what this is about. And listen, I want to thank everybody for joining me here. But before we do that, I want to show you guys some extra news that's going on in space so far. Yep. Where does it go? Here it is. We are going to be talking about Mars. Yep. Right now, Mars. Where did the page go? There it is. Mars. I just lost the page. Here it is. Mars. Nope. Okay, I'll just tell you what's going on. If you look up around northwest, you can see Mars at one of the closest approaches. It's closest until November. Yep, you can be able to see it closest until November. Another thing I wanted to show you guys is what's going on in the world. Recently, I was told that the Artemis Accords were signed. And people are like, what exactly is the Artemis Accords? I never heard of it before. Well, the Artemis Accords is nothing really new. It is the no fighting or littering. Yep, the NASA Accords. No fighting or littering when you get on the moon. You can't fight, you can't litter. It basically says secrecy is banned. All launch objects need to be identified and registered. That means no U.S. spy satellites, telescopes, no China satellites and telescopes. No other country can have any other thing. Anything on the moon needs to be registered and identified. Space shuttles must be universal, so everyone's equipment is compatible, which means we have to start working together. No more China race to the moon. No more Russia race to the moon. No more India race to the moon. No more America race to the moon. We need to do this all universally, planetarily. This needs to be a planetary effort, not a country effort. Because we have a planetary effort, we're going to have universal parts. Here's another thing. Historical sites must be preserved. You cannot trespass on the past Apollo sites. See, because rovers and other spacecraft cannot have the mission jeopardized by getting too close. And of course, you could be asked to leave. So how are you going to get kicked off the moon, huh? Let's see, Malcolm says, I've seen some arguments that we may be the first intelligent life in the galaxy or even invisible universe. Of course, I've also seen the opposite, as phosphorus is not very abundant. He is talking about the phosphorus that was found on Venus. I talked about it on my previous show. You guys can scroll back or down the video channels and check it out. Well, I want to thank everybody for joining me here today on this little show of What's Up with the Universe, Exoplanets. Next week, we are going to be talking about comets and NEOs. Yep, comets and NEOs. And speaking of NEOs, I want to show you this little page right here because there is a comet that's going to be possibly visible in the night sky. Let's see, where did I do that little tab here? Here it is. Oh wait, that's Mars, isn't it? Yep. Here it is. On October 18th of this year, if it's big enough, comet C 2020 P1, otherwise known as the Neowise comet, is going to be visible in the pre-dawn sky. Yep. All you do is look up east, and you will be able to see it, if possible. Comet Neowise. So we're also going to be talking about that next week on our show. So stick around, stick tuned. Yeah, stick tuned. We are going to be talking about comets and NEOs next week. So if you haven't hit that subscribe button, go ahead and do it if you want. If you want to know when I go live or post a video, ring that little bell. So in the meantime, I want to thank everybody for showing up. And remember, we always got to ask ourselves, hey, what's up with the universe?